All right, we've spent a lot of time on congruent triangles. Now we're going to look at similar triangles. And what we learned about congruent triangles is if two things are congruent, everything about them is identical. All their measurements are the same. Similar is a little bit different. When you use the word similar, like in conversation, you mean things, you're talking about things that look pretty much alike, but may have some little differences. And in geometry, the thing that can be different about shapes that are similar is their size. So similar figures, and in this case, similar triangles, look exactly the same. They're exactly the same shape. They're proportional to each other, but they're not necessarily the same size. So the picture over here on the right, you have the two yellow triangles. These are similar. They look very much the same, but obviously one is much smaller than the other. So what it says here is the corresponding angles are congruent, and you can see that in the diagram. We've got a couple pairs of congruent angles that are marked there, but the corresponding sides are proportional. We'll talk a little bit more about that as we go along. When we do congruent triangles, we've said that you can do rigid motions to go from one to another. You can do translations, rotations, or reflections. When we deal with similar triangles, we're bringing in our other transformation. We're bringing in dilations. So if I wanted to go from this big yellow triangle to the little yellow triangle, well, I would do like a translation over to the right. I'd do a translation down. And then I'd have to do a dilation to shrink the bigger triangle to make it the same size as the little triangle. So similar brings in dilation along with the other ones. One other thing before I go to this last statement, I want to point out the other diagram. One thing you'll see in similar triangles a lot is where you'll have a triangle within another triangle. So if you look at this diagram, triangle ADE is within triangle ABC. But we can still deal with them as two separate triangles. And that's a situation you'll see a lot with similar triangles. And especially when we get into like word problems, that's something that'll come up quite a bit. The symbol with similar is this one little squiggle. So with congruent, we had the equal sign with the squiggle on top. With similarity, we get rid of the equal sign. We just have the squiggle. All right, like congruent triangles, we have these different theorems for similar triangles where we can prove that they're similar. And we're going to go over three of them. There's only three. There's not five like we had with congruence. And the first one is angle-angle. So angle-angle similarity means if two triangles have two pairs of congruent angles, they are similar. We don't need any sides to do this. If you have two pairs of congruent angles, you're done. You can say they're similar. So we see that over here on the right. We see angle A and angle D are congruent. Angle B and angle E are congruent. So those two triangles automatically have to be similar. They're the exact same shape, exact same proportions, even though they're different sizes. And the third angle theorem, which we talked about in the last unit, is going to come into play here sometimes. Because if you look in the bottom left, we have two triangles. We don't know one angle in each triangle, but we can figure it out. And so what we can do is we can take 30 and 102 and add those together. And that's going to give us 132. We subtract that from 180. And we can find that our missing angle of EFG is 48 degrees. And you can see now that, okay, this has a 102 and a 48. So does LMN. It has a 102 and a 48. So if we add 102 and 48 and subtract it from 180, we should end up with 30. So if you know two angles are the same between two triangles, the third angle is also going to be the same. And so these end up being similar triangles. Even though when we first looked at them, we only had one pair of congruent angles, if we use the information we have to find the other angles, then we have angle-angle similarity. The other thing I want to point out on angle-angle is you may get a diagram like this one in the bottom right, and we have these little arrows, which you may remember indicate parallel lines. So when you have parallel lines and you have another line that connects them both, that line is your transversal, and you get special angle relationships. So right here, if I were to take this angle here, angle E, and this angle up here, angle C, those are alternate interior angles. They're in between the parallel lines, and they're on opposite sides of my transversal line. So they're congruent. I also see in this picture in the middle, I have vertical angles. So using things we learned way back about parallel lines and about vertical angles, I can say, okay, I've got two pairs of congruent angles. That means these triangles have to be similar. The next one is side angle side. That's obviously the same name as one of the ones we use for congruence. But for similarity, it works a little differently. So if you look at the top diagram here, we have a pair of congruent angles here in the middle, the vertical angles. So we got an angle. Our sides are not congruent, but they don't have to be. Instead of being congruent, they have to be proportional. And here's how we tell if they're proportional. We make ratios or fractions and see if those fractions are equal to each other. So here, with my two triangles, I'm going to match up corresponding sides. So my small side I have on each triangle would be the 18. That's the small side of BCD. And 27 would be the small side of BEA. So I'm going to make a ratio 18 over 27. And I'm going to do the same thing with the bigger sides. I'm going to do 24 over 36. And it really doesn't matter which number you have on top as long, that's a 36, sorry, as long as you're consistent. So I put the number from the smaller triangle on top, so you have to do that both times. If you put the number from the big triangle on top, you have to do that on both fractions. There's several ways to test and see if these are equal fractions. For this one, what I'm just going to do is simplify my fractions. So 18 and 27 will both divide by 9. 18 divided by 9 is 2. 27 divided by 9 is 3. So that becomes 2/3 when I simplify it. 24 and 36, I can divide both of those by 12, and I get 2/3 again. So I'm going to write that over there because something funny is happening with my pen. So they both end up being 2/3, and that means the sides are proportional. So if I were given these two triangles and were asked, are they similar? I would say yes, because of side angle side. I have a pair of angles in the middle that are congruent, and then I have two sets of proportional sides, because when I make them into fractions and I test to see if they're equal, they are equal. Let's do another one. This is a diagram where you have a triangle within another triangle. So if you look at the small triangle, we have a 9 and a 12. And if you look at the big triangle, what you have to do for the big triangle to get the side is add those two things together. So for BC, that's going to be 12, and that's going to go with the 9. And for the other side, I have to add the 12 and the 4 together. That's going to be 16, and that'll go with the 12. So now I'm going to take my pairs of sides and line them up. 9 goes with 12, and 12 goes with 16. And I almost wrote an equal sign, but I don't know they're equal yet, so I don't want to do that. We're trying to see if they're equal. Okay, 12 over 16. And I could do the same thing I did on the first example and just simplify my fractions. That would work. Another way you can do this is by cross multiplying. So cross multiplying, you take the denominator of one fraction, you multiply it by the numerator of the other one. So like 16 times 9, that's 144. Do the same thing the other way, 12 times 12, that's 144. Those are the same, those are equal. That means that the sides are proportional again. So I have two pairs of proportional sides, but to do side angle side, I also need an angle. And this is where our friend the reflexive property comes into play, because angle B up here at the top is part of both triangles. It's part of the little triangle and the big triangle. And it's congruent to itself by reflexive property. So this triangle down here, I would say, yes, those two triangles are similar by side angle side. We have an angle, two pairs of proportional sides. And just like when we were doing congruent triangles, the position matters. The angle does have to be in between the two sides that you're working with. All right, the third one is side, side, side. Again, that's one we use with congruent triangles. And again, the difference here is that we're not looking for sides that are the same. We're looking for sides that are proportional. So we have two examples here. And what we want to do is same thing, except we have three pairs of sides this time. So we're going to just kind of go around the triangles and match up the sides. So I'm going to take the 10. That's the smallest side of ABC. That's going to match up with 20, which is the smallest side of EFD. So I'm going to say 10 over 20. Then I'm going to do 15 with 25. And I'll do 21 and 35. Those are going to go together. That's the biggest side on each one. And I want to see if these fractions are equal. If all three fractions are equal, then I have a pair of similar triangles. And so this time I'm going to change them into decimals. So if I do, let's start with the right, 21 over 35. If you change that into a decimal, you should get 0.6. And by turning them into a decimal, I'm just dividing these. So you can divide them on a calculator or by hand, however you want to do it. 15 divided by 25 gets me 0.6. 10 over 20, though, gets me 0.5. And even though I got two 0.6s and those are the same, for me to be able to use side, 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 I would have to have three pairs of proportional sides. And my 10 and 20 sides, those don't work. They're not proportional with the other sides. So this would be a no. This would be one we cannot prove that they are similar with the information given there. Let's do the bottom set. Again, we're going to line these up the same way. Start with the smallest side, 14 and 10. And this time I'm going to put the 14 on top. You can do that as long as you're consistent. It doesn't matter which triangle's numbers you put on top. 21 is going to match up with the 15. And the 28 is going to match up with the 20. And again, we've seen three different ways we can do these. We can cross multiply. We can change our fractions into decimals, or we can just simplify the fractions and see if they end up being the same. I would say for side, 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 when you're dealing with three pairs of sides, either change them into a decimal or simplify the fractions. Don't do the cross multiplying because that gets complicated when you have three fractions. For the other ones, I would say just whatever seems easiest for that fraction. If it's something where you can simplify it really quick in your head, do that. If not, cross multiply it, see what you get. But here I'm gonna simplify these three because I can kind of see what they'll simplify by. 14 and 10 will both divide by 2. I get 7 over 5. 21 and 15, those will divide by 3, and I get 7 over 5. And then 28 and 20, I can divide both numbers by 4. I get 7 over 5. These are all equal. That means all three sets of sides are proportional. So this would be a yes by side, side, side. So let's look at some examples here. We've already kind of done some, but let's look at a few more just to become familiar with the types of problems. So on number 1, always look for things like vertical angles as usual, and we've got a pair of vertical angles right here. So we've got an angle, and then we've got two sides on either side of those angles that are marked. So we want to see, are they proportional? So I'm going to match up the 6 and the 21. I'm going to match up the 10 and the 35. Again, you match up the smaller side from each triangle and you match up the larger side from each triangle. And we want to see if they're equal. I want to just simplify these because I can see the 6 and 21, those both divide by 3. And I get 2 over 7. 10 and 35, those both divide by 5. And I get 2 over 7. And that's equal. So now I can say these are a yes, they are similar by side, angle, side. I have a side, got another side, I've got an angle in the middle. Side, angle, side. Number 2, kind of a similar setup. We have congruent angles, and we have two sides on either side of those angles that are marked. So we just have to see if they are, or if they're going to work, if they're going to be proportional. And if you line these up, what's going to happen here is you're going to have 16 over 87, and you're going to have 16 over 88. And if you want to cross multiply or change that to a decimal, you can. But one thing I will tell you is if you have, excuse me, if you have two fractions and the numerators are the same, but the denominators are different, they're never going to be equal. And same thing if the denominators are the same, but the numerators are different. So if you have one number that matches and one number that doesn't, they're not going to be equal. So this one be a no. Those triangles are not similar. Number 3. Oh, and I'm sorry. Excuse me. I swallowed a carrot funny. I'm not dying. I do need to make my little similarity statements, and I should have done that on number 1. I have STU is similar to, and now I got to match that up. So point S will go with itself. Point T is on the end of the short side of this triangle. So I'm going to take the short side of the other triangle. That takes me to Q. And then U and R, those are left over. Those will match up. On number 2, I don't have a statement because they weren't similar. On number 3, this is a triangle within a triangle. I can use my reflexive property here to say angle S is congruent to itself. One thing I need to do here, though, is I know the sides of the big triangle are 16 and 24. The little triangle, though, I have an 8. I need to know what this other side is. So what I'm going to do is I'm going to use my 24 and my 12. And I'm going to say, okay, if the whole thing from S to T is 24, and then LT is 12, if I take 24 minus 12, that's going to give me the part I'm looking for. Excuse me again, I'm sorry. But that's the old segment addition postulate from really early in the year. So now we can match these up. We have 8 and 16. We have 12 and 24. And I can tell right away, those are both going to be equal to 1/2 if I simplify them. If I change them into a decimal, they're going to become 0.5. And those are going to be equal. They're proportional. And I have that angle. I have angle S, which is congruent to itself. So I can say, okay, I got STU is similar to SLK. So L would go with the T, K would go with the U. And my reason here, again, would be side, angle, side. Number 4, right away I see vertical angles right here, so I'm going to mark those. I also have parallel lines. That's what those little red arrows represent. They're parallel lines. And so what I want to do is look for a transversal. So let's say MB, this big long side here, is a transversal connecting my parallel lines. And what that's going to do is give me 2 angles here that are congruent. They're alternate interior angles. So now I have 2 sets of congruent angles, and that's all I need to show that 2 triangles are similar. So I can say they are similar by angle, angle. And my congruency statement gets cut off a little bit here at the bottom. I'll just write it up here. So that ABC is similar to, and we're going to put A first, and that's going to line up with itself. B would match up with M because they're both connected to this these congruent angles I've marked with 2 arcs. And then C is going to match up with L. So ABC is similar to AML. Last couple examples here. Number 5 is going to be a quick one. I already know that angle F and angle V are the same because they're both 76. And I can see in the diagram I've got vertical angles in the middle, and those are always congruent. So that's 2 pairs of congruent angles. That's angle, angle. Remember, 2 angles is all you need to show that triangles are similar. Now what I would do is write my similarity statement. Okay, so E will match up with itself. F is at the 76-degree angle, which V is also at. So V will go with F. And then W is going to go with G. So EFG is similar to EVW. Last one. If this works, because I have no information about the angles, it's going to have to be side, side, side. So what I would do is I would set up my fractions. So I'm going to match up 30 and 50, the two smaller sides. 33 and 55. And 39 and 65. So 30 and 50, I can simplify that pretty quickly. Just divide those by 10, I get 3/5. 33 and 55, same thing. I can divide them by 11 and get 3/5. 39 over 65 is a little harder to see. So there's a couple ways you could do this. One thing you could do is, once you got 3/5, just change that to a decimal. It's going to be 0.6. And then if you have a calculator handy, take 39 divided by 65 and see what decimal you get. The other thing you can do, if you see it, is 39 and 65 actually both divide by 13. And when you divide them by 13, you do actually get 3/5, which is 0.6. So either way you do it, you will show that all three sets of sides are proportional. They all reduce or simplify to 3/5, or they all turn into 0.6 as a decimal. So this would be yes, these are similar by side, side, side. We have three sets of proportional sides. And so when we do our statement, CDE is similar to, well, C is between the smallest two sides. So it matches up with T, which is between the smallest two sides on the top triangle. D is between the two larger sides. So that's going to match up with U. And then V and E are the only ones that are left, so they match up together. So that's similar triangles. So a lot of it is similar to what we do with congruent triangles, but there are some key differences, because when we're working with the sides, what we're looking at is, are they proportional, not are they the same? So there you go.